Thanks, Bruce. Bruce is one of my oldest friends in physics and one I admire a great deal, so I really appreciate that introduction. I'm going to tell you a little bit tonight about a theme that was really the sort of the thesis of Carl Sagan's Origins presentation on public TV some decades ago. And the major theme of that was our place in the cosmos. We're on a very small outpost here on Earth, but we learned a great deal about its inner workings. And this has been an area of physics and astrophysics over the past 2 decades that's made some marvelous discoveries. Some of those discoveries are to realize that there are a lot of things out there that we don't understand, haven't even identified yet. So tonight, what I'll try to tell you about is why is there something out there instead of just nothing in our universe? And this is a question of why our universe is not just full of radiation, but instead has interesting things like planets and stars and galaxies. And what creates it something? This is really topical because just a couple of months ago, CERN announced that they had seen a particle that might be the Higgs. And we think the Higgs, the God particle, might be the source of at least some of the mass that we see about us. And then I want to talk about what's even much more mysterious, what we haven't discovered. These are the dark worlds, things we cannot see, but we think we know that they're there. And they include the neutrino, which is the first evidence we have of something's wrong with our standard model of particle physics. Still darker, the dark matter. We know that we're not the dominant form of matter in our universe, but we don't know what that dominant form is or what its properties are. And still darker, this relates to what Einstein considered his greatest mistake, which may actually have been his greatest insight, that the vacuum itself is a form of energy. And finally, I'll try to wrap up with a couple of comments about our just so universe, how curious it is that all the parameters are set in just such a way that we can actually exist here on Earth. So I'm going to start with this picture, which gives you a feeling of how two things happen. One is the evolution of our universe. As time goes on, we start from a very simple system of elementary particles and very high temperatures. And then as the time evolves, we get into a number of different eras where we create nuclear physics, atomic physics, where we begin to see structure, the first stars and the first galaxies. And then finally to the rich complexity that we have today when we look in the night sky, all kinds of stars that are of different generations. And what the astronomer and the astrophysicist tries to do is he tries to go in the other direction. The physicist is interested in going in the other direction because it's the way of getting at higher and higher energies. So we build accelerators. Those cost a lot of money. That's one way we have of getting to high energy and looking at small distance scales. But the other way is to use the cosmos. We know the cosmos was very hot at the beginning, and so the farther we can reach back in time, the more we can learn about the physics that may have operated at those times. We look back in time by trying to gather evidence from the night sky, and that evidence is primarily, for most part, optical photons that come to us from distant stars. Fortunately, the speed of light is finite, so when we gather light from very distant objects, we're actually looking back in time, because the point at which that light was emitted was many years ago. So I'll tell you a little bit about the scales of some of the things we've been able to do by looking back with various kinds of optical and other devices. So let's just look at that time, that period of time from the Big Bang until now. We think it encompasses about 13.7 billion years. And what are the important events along this timeline to kind of place ourselves in the context of cosmological history? Well, the most important thing, of course, is us. And unfortunately, my computer doesn't have enough pixels. And so I have to put us at the very end because we comprise 1/10 of a pixel along that line. Homo erectus moved out of Africa about 2 million years ago on a 13.7 billion year scale. So we haven't been around very long. It's also going to be surprising for folks that live in Tucson, but we also live in a time when the universe is extremely cold. If you go out into interstellar space and measure the temperature, the radiation, it's 3 degrees above absolute zero. And so the universe has cooled a great deal since the early times. The next probably interesting period is the birth of our solar system. That occurred about 9.1 billion years after the Big Bang. So it's been around about 4.6 billion years. It's a very interesting process. A volume of hydrogen and helium-dominated gas contracted under gravity. And that contraction stops when you press the gas together strongly enough that it can ignite. So the proto-sun ignites and starts burning protons into helium. And those thermonuclear reactions are actually the source of the solar energy we see, as well as responsible for a lot of the chemical diversity in our solar system. We also have a process in the end stage of this formation of the sun, the protosolar disk, where the planets condense out. And they condense out at different points. And where they condense out affects their chemistry. So stars like the Earth, rocky stars rocky planets like the Earth are very different chemically from the gaseous giants like Jupiter and Neptune. The sun is one of 300 billion Milky Way stars out there. Just in our galaxy, there are 300 billion neighbors we have. Unfortunately, it has about another 5 billion years of thermonuclear fuel left, so it'll be around for some time before it turns into a red giant. The next stage is go back not to stars like our sun, which are second or third generation, but to the very first stars that formed. Those occurred much earlier. We think the first stars formed about 200 to 300 million years after the Big Bang. And they seeded through the first stars were probably very massive, so they evolved quickly. Unlike our sun, instead of living for 10 billion years, they may have lived for 10 million years. And then these massive stars blow up in great explosions, and those explosions themselves seed the birth of new stars. So this is the process by which the universe begins to produce complex structures, large-scale structure. And at this period, almost everything we study in high-energy astrophysics, light, ionization of atoms, magnetic fields, shock waves, acceleration of particles, they're all associated with these objects, the stars and the galaxies they live in. And the Milky Way, our galaxy, and our location in that galaxy circled there, is one of 10 to the 11 galaxies in the visible universe. So if you fold that with the fact that we're one of 300 billion stars in that galaxy, you begin to see what our place in nature might be. The temperature when the first stars formed was a little bit warmer, about 20 degrees above absolute zero, but still quite cold. And then the next interesting phase, I would go back and say, is the beginning of atomic physics. And so you notice now I've taken that timeline and greatly expanded it by a factor of about 10,000. So it encompasses about 1 million years instead of 13 billion years. And this is the process by where in the initial state, which includes a plasma of basically protons and a few alpha particles and lots of electrons existing in free state, so all the charges are separated, cools down enough so that those electrons have to begin to capture onto the protons to form neutral hydrogen. And this is really important epoch for astronomy. Once that's done, it's taken the plasma, which used to consist of charges, into a different plasma that consists of neutral hydrogen, and so none of the objects are compact, but none of the objects carry a net charge because the sums of the charges in a hydrogen atom are zero. And what that means is that prior to producing atoms, we had a universe that was opaque because photons scatter off of charges, and so photons try to migrate in that charged plasma. They cannot. When they suddenly reach a temperature where atoms can form, those electrons jump down into their orbits around hydrogen and emit a photon, and that radiation is now released because it sees itself surrounded by other neutral objects. So we can actually see the light that came from that period when the atoms first formed. And a picture of it is shown there. It's not only can we see it over the entire night sky, it's not a radiation that we see through a telescope. It's been so far away, and Einstein taught us about the effects of gravity and Doppler shifting, that light is now shifted, and so it's no longer optical photons, no longer EV photons, but microwave photons. So we measure those with microwave antennas, and we can measure it so well that we can see small deviations in the temperature of that radiation, depending on where we look in the night sky, of less than 1 part in 10 to the 5. And we see our variations in temperature at that level. And those tell us about what the shape of the universe looked at that time. We already know that the universe was, although there were no stars, no galaxies, nothing that we would recognize as real dense objects, nevertheless there were regions of overdensity and underdensity. And when these photons pull out of regions of overdensity, they have to work harder against gravity, and they're shifted more, Doppler shifted more than those that come out of other regions. And so we can get the feeling for what the shape of the universe looked at just 380,000 years after, after formation. Afterward, though, once this microwave radiation is formed, there are no stars. There's nothing, no galaxies. There's nothing to produce any kind of radiation. You've cooled down into this neutral hydrogen, and that's all you have. And so we call it the dark ages that appears after this point. And the universe stays dark until the stars turn on 200 million, at time 200 million years. The next epoch, we have to, again, expand that scale. Now it's by a factor of 100 billion. So we go back and look at the first 5 minutes. And the same process that occurred in the atoms now occurs at the nuclear level. So when it was very hot, we had free protons and neutrons. They formed the plasma. That was the state of the matter. When we cool down to a temperature characteristic of this time, then the protons and neutrons can combine and to form alpha particles. And this is really important for all the chemistry that we know about. And I want to discuss this because it was the first really quantitative result in cosmology. It was a guide for a lot of the things that we've done since. And it gives us an extremely important number that characterizes our universe. So let me walk you through this in a little more care. So as you cool things, then matter tries to settle in its lowest energy state because it cannot, from the thermal bath, take up enough energy to jump to a higher energy state. And if we look at the proton and the neutron, we find out that the neutron is actually heavier than the proton, and yet it can decay into a proton through the process of beta decay. And so the naive expectation, if you thought about those two things, was you might start with a bath at very high temperature that was equal number of neutrons and protons because the temperature is much higher than the mass difference. But as you cool down, you would expect to wind up with a plasma of nothing left but protons. And, but today's universe is not full of just hydrogen. It has more diversity than that. So what really happened? And so if we take a look of a system like this of nucleons and watch it, you can see that you'll see the green guys disappear slowly. So you're watching this process of beta decay. And so if nothing else intervened, all the protons would eventually turn into, all the neutrons would eventually turn into protons. You'd have hydrogen only. But fortunately, this boring outcome is not what we experience because of some interesting nuclear physics. So again, this is a picture of that same process here. And we have, we have 2 free neutrons up here, and they can decay. One of those guys can decay into a neutron and a proton. And that other neutron can then decay again into 2 protons. And so this is the process that we just examined, but for a collection of about 10 nucleons. But in fact, if you form a state of a neutron and a proton, something else can happen. Those guys can actually merge and form a nucleus called deuterium. And deuterium is bound by about 2.2 MeV. So the lowest energy state is not a bunch of protons sitting in free space acting as a plasma. It's actually neutrons combining with protons to form deuterium. So it's deuterium that should happen. And this is interesting because this mechanism is actually the mechanism by which is responsible for the chemistry of the Big Bang. That's why we have helium and lithium from the Big Bang. But it's also why we have carbon. It's also why we have oxygen, because all the stars use this process of forming tightly bound nuclei to release energy. So solar energy, at its core, is really the energy that you get by building more and more complex nuclei that are tighter, more and more tightly bound, that release energy. So we can do a really, once we realize that this is the physics of what must have happened in the early universe, we can do a really interesting calculation. We can just look around us and count how much hydrogen is in the universe and how much helium. We can do that pretty well by looking at old stars. We find out if we count by mass that roughly 25% of the mass is helium and 75% of the mass of the universe is in hydrogen. And so we make a picture of that. Since hydrogen is free protons, we have a bunch of free protons here, and I've written down, I guess, 12 of those. And then 4 of the nucleons, 2 protons and 2 neutrons, combine to form an alpha particle. So this would be an inventory of nucleons, with 4 then settling in and forming a helium nucleus that would account for a universe that has 75% hydrogen and 25% helium by mass. Now this is interesting because you essentially, if you think about this, you now have a clock, because we just described the fact that these protons were decaying into neutrons. They decay in conditions in the early universe on time scales on the order of a minute. But in fact, what we find is today we have neutrons left around. So at some point when the ratio of protons to neutrons was this ratio of 1 to 7, because that ratio is what allows you to form 25% by mass helium, 75% by mass hydrogen. When the ratio of protons to neutrons was about 1/7, then that's when deuterium formed. So we've just come up with a clock, just by observation, that that must be the time when nuclei formed in the early universe. So that's nice because we can now do another calculation. We know how deuterium is created. That's a proton and a neutron coming together, forming a deuterium, and then spitting out a photon. And we also know how deuterium is destroyed. That's a photon from the thermal bath that all these nuclei live in because the early universe is hot, hitting a deuterium nucleus and breaking it back up into a neutron and a proton. Now, when the universe is young and hot, then there are lots of very energetic photons, and those photons can easily break up deuterium. As you cool down the universe, fewer and fewer of the photons have enough energy, that the 2.2 MeV that's required to break up a deuterium nucleus, to actually do the breakup. So the reason that deuterium survives eventually is that the universe cools enough so that a very small fraction of the photons are energetic enough to break up the nucleus. We can define the time that deuterium is formed in a different way. We can say it's when these two reactions, since this reaction is changing very, very rapidly as the universe is cooling, it must be the time when those two reactions are essentially equally fast. Now that's interesting because if you look at this first reaction, its rate will depend on the number of neutrons and protons you have around to interact with. But the second guy will depend also on the number of neutrons and protons because the deuterium is there, but also on the number of photons. So if you require these two rates to be equal, you learn something about the number of photons versus the number of nucleons. And so we can go through and do this in more detail. I won't do it here, but you can kind of see the basic idea. When you solve this problem, you find out a very interesting number. It's the ratio of the number of nucleons to the number of photons in our universe, the nucleon density to the photon density. And we actually know the photon density, so in fact we know the average matter density in the universe from this very simple argument that 25% of the matter out there is helium and roughly 75% of the matter is hydrogen. And what do you find? Well, you find out when you do that calculation of the decay that this process must have occurred 3 minutes after the Big Bang at a temperature of roughly 1 billion degrees, which is actually quite cool, much less than the 2.2 MeV that it takes to break up the deuterium nucleus. And you do that by nuclear forensics. You look at the elements that were produced in the Big Bang, helium-4, deuterium, helium-3, lithium, and then you find the value of the photon, the baryon to photon, nucleon to photon ratio that produces a requisite amount of those elements. And you get a surprising number out of this. You find out that the ratio of nucleons to photons in the universe is one nucleon for every billion photons. So we'll come back to that number in a little bit. It's a very important number. And finally, there's one more stage I'll talk about. This is where we get to the point of sort of ultimate simplicity from our point of view, which is the elementary particle universe. Even the proton and the neutron are composite particles. They're the last particles that are complex. If we go to a period when we don't have protons and neutrons anymore, but only have their constituents, those are the quarks, the up and down quarks. If we go back far enough so that the plasma is hot enough, the protons and neutrons dissolve and form instead this quark plasma in space. And that's the point where everything that exists around you, there's no structure whatsoever. Everything is an elementary particle. Everything is living in a plasma. And we can work out what time that occurs. And it's very, very early. It's at a time of about 30 microseconds after the Big Bang. So at that point, after that point, you actually have nucleons. Before that point, nothing but the elementary particles, the things we study at accelerators. And you can also put a limit on how far back we can tell this story, how much confidence we have in going further beyond that point. How far back do we understand the particle physics? And since physics is an experimental field, we understand what goes on in this elementary particle universe until we get to the point that we no longer can do experiments. And that's at an energy that corresponds to a time 10 to the minus 12 seconds after the Big Bang, where the universe has a temperature of 10 to the 16 degrees K, which corresponds to an energy of about a TeV. And why that's an interesting, beyond that, we have no experience with the physics, so we really don't know what's going on. And the reason we have no experience with the physics is that's the biggest accelerator we've yet managed to build, and its energy is a TeV. So we can get to a TeV, make sure we understand how elementary particles behave, but much beyond that, we're doing theory instead of really experimental physics in some way. And you can see from the size of that, of CERN, that this is a major enterprise. Billions and billions of dollars go into building something of this sort. And the kinds of detectors that you have built are of the same kind of scale. So this takes teams literally of 2,000 and 3,000 people working together over many years to be able to do the science at this scale. So that was kind of an introduction to all the phases, expanding on that initial picture of what the expanding universe looks like, from this very hot point-like universe to this very cold universe with lots of complexity that we live in today. And this evolution in time is fundamentally about matter. So we've seen going from fundamental particles to nucleons and then to atoms, and then real structure of the sort that we would recognize, the first stars and galaxies, and then finally the complex structure of today's universe, where you have not only stars, but you have stars made out of the material that was produced from previous generations of stars. So our incomplete understanding of matter is actually at the root of some of the puzzles that this picture, this cosmological evolution, actually presents us. And I'd like to talk about those now because they are kind of fascinating. This first question is, why is there something and not just nothing in our universe? Why are there any massive particles in the universe instead of just radiation only? And this comes about because all theories that we know how to construct in particle physics have a property that for every particle, there's a corresponding antiparticle. And that antiparticle is just like the particle, except it has all of the opposite charges. So an example is that we have an electron. Electron is a particle that has a certain mass m, and it has a charge minus an electron charge. And there's a corresponding particle, a proton, that has the same mass but has the opposite charge. Likewise, we have an up quark, one of the constituents of the proton, has 2/3 of a charge as its charge. And there's a corresponding anti-up quark, which has a charge of minus 2/3. And a down quark, the other constituent of the proton, minus a third charge. The anti-quark, the down quark, has a plus 1/3 of a charge. And it's just like in Star Trek, when you put matter and antimatter together, they annihilate and form radiation. So one would expect, since all of our theories are mostly symmetric under particle and antiparticle exchange, that the hot early universe probably was equally populated by particles and antiparticle. So as you expand the universe, this would be an example of a particle and an antiparticle. They'd wander around, but eventually they'd come together. When they come together, they annihilate, and all you get is radiation. Now, we just did this calculation. That's why I went through the Big Bang in some detail, is we know that it didn't completely annihilate, that the ratio of radiation to matter is not infinite. It's instead 10 to the 9. We had 10 to the 9 microwave photons for every nucleon. So somehow this is not what happened. There was a tiny excess of matter in the early universe over what we call antimatter. And that's the stuff we're made out of, the residual part. Everything else annihilated. Probably initially you had the same amount of matter as had photons. They came together and completely annihilated, but there was a small excess of the matter. So we know what's required. There are really 3 conditions for having that antimatter excess. And the one that's most interesting to have this asymmetry between matter and antimatter in the early universe is you must have a theory that's not invariant under time reversal. That is, the basic laws of physics cannot be invariant under time reversal. So this means that if you took a picture of elementary particles scattering and then made a movie out of that and ran the movie backward, that you can tell that the movie's running backwards and not forwards. And that should be very surprising. No one suspected that time reversal would be seen in particle physics, but it was actually discovered quite a long time ago, in around late 1950s, in an experiment done at an accelerator for an entirely different reason. The problem is that the amount of time reversal violation that we've seen so far in physics in our standard model is really tiny. And if we take that amount of time reversal and we do our cosmology, we don't produce the necessary asymmetry in the matter. There's not enough time reversal violation. So this tells us that there's some undiscovered interaction out there that we haven't seen yet that must have operated in the early universe and that must be responsible for why we're here, but we really don't know what it is. Actually, we have some pretty good ideas today of where that physics might reside. And within the next 10 years, we're going to be doing some experiments to see if we might be right on that. I won't tell you more unless there's a question on this. I want to go on to this other interesting question. Since we have some matter, well, what do we mean by matter? What is this something? And this is a really interesting connection between mass and spin and this new particle that's maybe been discovered at CERN called the Higgs boson. So this answer is connected with this notion of spin, and I'm going to try to explain it with this soccer ball here. If you have a soccer ball and you have you point it to an axis, you can spin the ball around that axis. But because it's a big soccer ball, you could choose to spin that ball around any other axis that you might want to do it. That's true with any macroscopic particle. And it turns out in quantum mechanics, there's an analogous spin. You shouldn't think about it quite like this, like a soccer ball. It's an intrinsic spin that elementary particles have. And unlike this case of a soccer ball, that spin can only point in one of two directions. And we usually choose, just because it's simple, we choose our axis along the direction of motion of the particle. And so we talk about two spin directions. Either the spin is pointing along the direction of motion, we call that a right-handed particle, or the spin is pointing against the direction of motion. The particle has a direction of motion that defines the direction, and then it's only two possibilities for that spin. It goes this way or this way. Can't go anywhere in between. And so that's an intrinsic property of elementary particles that was first really understood by Wolfgang Pauli a long time ago. Still a little bit mysterious. And it's connected with this Higgs. In the standard model, turns out you might think we could just go into our standard model of particle physics and we can measure the masses of the various particles, and then we could just write those numbers down in the standard model and we'd be done. Turns out you can't do that. You can't just assign masses in the standard model. It wouldn't be mathematically consistent. You have to find a way to dynamically create these. It has to be part of the theory that the mass is generated within our standard model of particle physics. And this is accomplished by theoreticians a long time ago, not by experimentalists, by theoreticians who said the only way we know how to do this is to assume that space is full of a field that we haven't identified yet. And what gives mass to particles is the fact that those particles scatter off that field. And if you have a particle that's massless, and we have a good example of a massless massless particle here, which is a photon. A photon is massless because for some reason it doesn't ever scatter off the Higgs field. So if it flies through space, you wind up getting something of this sort. Just goes right on through, everyone's happy. Passes through the Higgs field without interacting. But suppose you have a particle that has a mass. Could be a quark or electron. What does the Higgs field do? Now look at the spin. The spin is going to be pointed along the direction of motion of this particle initially. Travels along, and then the property of the Higgs is that when it interacts with that Higgs field, it flips the spin. And now it's going to go with the spin pointing in the opposite direction. It's going to hit that Higgs field again, and now it's flipped the spin again, and it's with it again. And a particle, when you say a particle is light, what it means is that it scatters on the Higgs field only ever so often. And so this is a picture of a light particle because it only scattered twice while it exited our slide here. Now, but for a heavy quark, the picture's a little bit different. It propagates, flips its spin, propagates with a spin going the other way, hits the Higgs again, propagates again, has flipped its spin, flips the spin again, propagates over and over again, doesn't get very far. That's a particle that's heavy. So how frequently, how tightly you are coupled to the Higgs field determines your mass. And this way we can generate the masses of the various elementary particles. So until recently, the Higgs field was actually just a theoretical construct. It was a way out of all the mathematical conundrums we had in the standard model. It was the last little piece of the model that was fictitious in the sense that we didn't really ever, we hadn't actually identified that Higgs particle. It had a lot of people were suspicious about the Higgs. It sounded like it might be a cartoon about something else we didn't understand. It sounds very spookily like old notions of the ether and so forth that used to exist before Einstein. But this changed with the discovery at CERN just a couple of months ago. They actually produced, by having very high interactions at CERN, they actually produced the particle that mediates this field of the Higgs boson. So On the right there, there's a picture of one of the decays. We don't technically actually know it's a Higgs. It's a particle that has about the right mass for the Higgs, and it has properties that seem very similar to the Higgs. But there's going to be a couple of years of study to make sure that this really is exactly the Higgs particle as predicted by the standard model. But its mass has been measured. It's about 125 GeV. So you need big accelerators to produce this guy. And in this picture here, this picture used to consist of all the particles in the box, and the Higgs boson was sitting at the bottom undiscovered. For that reason, Leon Lederman from Fermilab wrote a book where he called this the goddamn particle. And the editor said that was a bad idea, and so he made it the God particle. So that's why this became the God particle. But the God particle is the missing ingredient. It gives the masses that you need for all the particles you see in that table and kind of explains the basic properties of our otherwise well understood table of elementary particles. But it's not the whole story. The dark worlds. We're now going to turn to stuff that's really pretty spooky. Mass mechanisms and matter that we do not understand. We've also learned some things about the neutrino, and then I'll tell you about dark matter and dark energies. Now, issues very similar to the Higgs field troubled Einstein. He really wanted to understand the shape and history of the universe, just the problem we're discussing here. He wanted to know why the universe looks like it looks. He wrote down some equations. This is general relativity. And conceptually, they're actually pretty simple. Computationally, they're pretty hard to solve. But what he said is that the presence of matter in space actually warps space-time, changes the geometry. Instead of having a nice flat space, like we're used to thinking in Euclidean geometry, you put matter in, and that matter actually changes the shape of the space. And particles, including a light particle, follow that curved space. And so straight lines become, it's like living on a surface of a balloon. Our universe is not a flat table, it was 2 dimensions, but instead some surface of a balloon. And so he wrote down an equation that basically says the geometry, that's the left-hand side of the equation, equals, it's the mass and energy on the right-hand, mass and energy and momentum on the right-hand side that curves the geometry. So he's able to relate how much curvature you have to how much matter you have in a given position. And again, particles then travel in general relativity, not in straight lines, but along these trajectories in curved space that come from solving this equation. So the curvature is the path. This is really an interesting concept now because it tells us that we can use geometry, we can use the curvature of light as it passes around some object to actually weigh that object. We can figure out how much mass is there because we can see how it warps geometry. Now, we have a theory of particle physics, the standard model, that has survived every laboratory test that we've been able to do for the past 30 years. And the Higgs boson, as I mentioned, was the last piece of the kind of puzzle that was awaiting verification. It looks like we're a long ways along there. But when we actually confront cosmology with that table, one of the particles stand out. And those are the neutrinos. I haven't made a big deal about these up until now, but now they should be featured. And so we have the up and down quarks that make the proton, and we have the electrons that we need to make the hydrogen atom. And what are these guys? These are the byproducts of the weak interactions. And so when we were decaying that neutron to a proton, a particle that was emitted was a neutrino. And the neutrino is sometimes called the ghost particle because it's so darn hard to see. Right now, for example, there are about, I guess about 1,000 billion primordial neutrinos going through every square centimeter, everyone in this room, and you never notice it. There are almost as many of neutrinos from the sun that are doing the same thing. So just zillions and zillions of these guys go through you during your lifetime. The average, probably about 5 people in this room will actually have one neutrino interaction before they die, but you'll never notice it. You know, one of your cells will actually interact with a neutrino. Very rare. They pass through matter. They can pass through light years of lead without interacting. That's why they're kind of hard to study. The standard model, this model with all this elegant mathematics, tells us that primordial neutrinos are massless. And so they do very little in Einstein's theory because they have no mass, and so they do very little to warp the shape of space. They're just essentially just like photons. In fact, they're the same number of neutrinos in this room, more or less, as there are microwave photons from the Big Bang. Why are they massless? Because in our standard model, neutrinos only come in one spin state. So this is why they have to be massless. We said what the Higgs boson does is it takes a particle with a spin going with or against its direction of motion, and then it flips that spin. The neutrino in the standard model only comes in one spin direction. A neutrino is always left-handed. its spin is always pointed opposite the direction that it moves. This is a big surprise. We didn't think that was going to be the case, but we produced these guys in the laboratory, and we measured it, and by golly, every time you produce one, that's the direction of its spin. So there's no debate about it. To the extent that we can measure, we know that's the case. So there's no spin state for the neutrino. So what happens if you try to give it a mass by the Higgs mechanism? So we know how to do that again. We let that neutrino travel. Doesn't interact with the Higgs mechanism. Okay, that's good. But suppose you actually did go back and say, what happens if I try to scatter off the Higgs field? The problem is, if you scatter off the Higgs field, you have to flip the spin, and that changes the left-handed neutrino. Neutrinos are always left-handed into a right-handed neutrino, and there is no such particle. So that Higgs interaction is not allowed. That's why the neutrinos have to be massless in the standard model. But it turned out that that was wrong. Why? Because physics is not a field for theorists. It's a field for measurement. So people go and measure neutrino properties and find out what happens. These are two absolutely extraordinary experiments. The one on the left, one on the right is an experiment that was done in Japan. That detector contains 50,000 tons of water, a huge 50-meter across a tank. It's surrounded by 1,000 Hamamatsu phototubes, big as a TV, that can see small interactions of neutrinos in that water. In that boat, those are graduate students, and what they're actually doing at the moment is they're finishing the detector, so they're filling it with water slowly, and the job of the graduate students is to go around in their boat and clean off the glass surface of every one of those phototubes, all 11,000 of them. And then when the water gets all the way to the top, they popped out through the porthole on the top. And so that's what being a graduate student's like. The one on the left is, in a way, even a more amazing experiment. This was done in Canada by Canadians, primarily Canadians and US physicists. It was a ball somewhat smaller than this one here. It had about, the central part of the detector had just 1,000 tons of water in it, and then surrounding it with another 7,000 tons of water. And just like in the Japanese experiment, there's an array that they built with phototubes that look inward at the water. Now, this experiment was built at 2 kilometers underground. That is a long ways underground. They found a very special mine in Canada, the Inco nickel mine, but that was that deep. And the mine was really helpful in producing this detector. Now, what's special about this detector is they used a different kind of water. The water in the detector on the left is not ordinary water, it's heavy water. So they've replaced the hydrogen in water with deuterium. That's $1 billion worth of heavy water. And why this experiment was done in Canada is Canada builds reactors, and the reactors use heavy water, and the business has been slow, so they had a whole lot of heavy water flying around. And they gave it to the scientists, provided the scientists would get the necessary insurance that they wouldn't lose the $1 billion of heavy water during the experiment. That experiment ran for about 15 years. It's now closed down. They're building a new experiment in that same site. What these experiments found out was that neutrinos change. They're produced in the center of the sun. That's the neutrinos that they were measuring. And we expected to measure them when they got on Earth. But they found out that the neutrinos had actually changed from one type, the electron type, into a combination of muon and tauon neutrinos. Now, if neutrinos were massless, Einstein also told us that if you watch somebody going by you, and he holds a clock, and as he goes by you at a very rapid rate of speed, and you look at the clock will appear to you to run slowly. And if that guy is going by you at the speed of light, and you look at his clock won't move at all. If his clock is not moving at all because he's going by you at the speed of light, he can't change. There's no concept of time anymore. That's what Einstein taught us. So if you have a particle that changes as you watch it, it can't possibly be massless, because change means something's happened at some time. There must be a clock running somewhere. So in fact, this was a proof. Much more detailed than that, we actually know exactly a lot about the masses from these experiments. So despite the standard model, neutrinos are massive. So we have a dilemma now. Neutrinos appear to come in only one spin state. We proved that experimentally. But they also have mass. We proved that experimentally. So how do you get out of this? Because the Higgs is what produces mass, and the Higgs can't give these guys masses. So you just kind of play around with it a little bit, and you come up with something that, like this. The left-handed neutrino travels through space, interacts with the Higgs, but turns into something else, not a neutrino. And that guy's probably really heavy, travels a little bit, again interacts with the Higgs, flips back again, and he's left-handed again. So two Higgs interactions with something else inside, something we haven't identified yet, could explain how this neutrino gets a mass. And in fact, if you work this through, you would discover that this must mean the neutrino is very light. And in fact, the neutrino is very light. And so we don't see this intermediate new state because it comes and goes almost instantaneously. Neutrinos have a mass much smaller than other standard model particles, so that's consistent with that. This is in accord with quantum mechanics. In quantum mechanics, you can be in a certain state with a certain energy, and then you can jump to an incredible energy and back down again, provided you do it really quickly. It lets you cheat, doesn't have to conserve energy at all time. That's great. So you can violate energy conservation. The underground neutrino experiments we have done suggest that this new state has an incredible mass. It's 10 to the 15 GeV. Translated, that's a million times the energy of CERN. So if whatever that particle is, we're not going to see it at CERN, and we're not going to see it next generation CERN or next generation CERN. We're never going to see it in an accelerator. It's too energetic. We can't produce those energies in the laboratory. And the mass scale, but the mass scale that came out, this number, 10 to the 15 GeV, was really exciting because if we look at theory tells us that there's a very important scale just about at this scale. It's called the grand unified scale. And that's where we think all the three fundamental forces, the weak force, the strong force, and the electromagnetic force, actually merge into one force. So the thought is that there could be another theory way out there, and we're actually learning a little bit about it by doing these very subtle experiments with neutrinos. So that's really neat. So this tells you, the takeaway here is that it's not all Higgs. There's another mass generation mechanism out there. Has to be because of the neutrinos. And we had to figure out what that guy is. Now it gets even a little bit darker. This is dark matter. Because neutrinos have mass, they become significant. It's what we call dark matter. You can't see them. They're filling this room. There's no possible experiment we know how to do to detect them. The low energy ones that come from the Big Bang. But if neutrinos have a mass, then there's mass in the universe associated with those neutrinos. So they affect the geometry. And it turns out within the next 10 years, as we do really careful measurements in astronomy and astrophysics, we should actually see the effect of that neutrino mass on changing the shapes and the structure of the galaxies in our universe. It's really quite amazing, as well as its effect on the cosmic microwave background radiation. But it turned out, just like this picture shows, that the neutrino dark matter, the last thing that we did, the last candidate to be massive in the standard model, it's only part of the story. There's a lot of other mass out there, the rest of the dark matter, that is curving space-time. And the neutrinos are just a tiny part of this, and what we haven't discovered, the rest of the dark matter, is much larger. And how do we know that? There's lots of different ways, but this is one of the most spectacular pictures. This is a collision of clusters of galaxies. It's called a bullet cluster, and there are regions of pink and regions of blue. The reasons, this is kind of, NASA colors these up so we can see them. They don't really look like this, but you know, it really helps guide the eye. So the pink part is the matter from the real matter that we know about from the two colliding galaxies. And so it's a collision, and because when they collide, of course, they interact, and that slows them down because of the collision. You collide two things together, they slow down, and so you get kind of this mass of pink stuff in the middle from the collision. What's the stuff on the blue? We see that, the only way we can possibly see it, we see it by gravitational lensing. We're watching the curving of space-time due to the fact that there's extra matter there, and figuring out that there's more matter than we're seeing. So in our optical telescope, we see the pink. When we do the gravitational lensing, when we use Einstein's technique to see mass, we see the blue. And what do you see? The blue has passed right through one another. So there was dark matter and dark matter surrounding each of these galaxies. The galaxies collided, the visible matter stayed in the middle, and the dark matter just passed on through. So we know there's some stuff there. It's very important gravitationally. Actually, it's important in producing these galaxies, but it doesn't interact very well because otherwise it would stop in the collision. So it's a pretty dramatic demonstration that there's something out there that we've completely not been able to identify. And in fact, since we've done the calculation of how much matter came from the Big Bang, we got our 10 to the minus 9, we know how much real matter there is, the matter that's important to us. We can compare our matter to the rest of the matter, and we find out that we're 4%, and the rest of the matter is 22%. So that's us, everything in this room, everything you know about, all the stars and all the galaxies. That's the stuff we haven't even identified yet. And we know some properties of that from various tests. We know it's probably a stable particle, possibly a long-lived particle. It's not relativistic. It's not moving fast like neutrinos. It's cold or perhaps warm. It's gravitationally active. We saw it there in the bullet galaxy. It interacts very weakly with visible matter, and it interacts very weakly with itself. So we know a lot about this, but we just don't know what the heck it is. There is no candidate in our standard model of particle physics to explain what that is. It's something totally new. And in fact, one of the things that theoretical cosmologists do today is they build a model of the formation of structure in the universe. And they have, just like cooking, they find out they had to put in just the right amount of dark matter into the recipe to form a pattern of galaxies that matches what we see in the night sky. So this is a simulation done by the Bolshoi collaboration, and they picked just the right amount of dark matter, that 22%, and it's produced this pattern, and this pattern matches what we see in astronomical surveys extremely well. In the case of neutrinos, at least we had a particle in the standard model to deal with. Here we don't have a particle, so we're really stuck trying to figure out what this guy is. And just like in neutrino physics, we're trying to see it in various ways, but probably the most important way is to build detectors, again, deep underground, very quiet places, and hope to see dark matter scattering. We know it scatters only occasionally, but dark matter scattering off ordinary nuclear matter to see the recoil of that nuclear matter. That's the only thing we can do, is when it bumps ordinary matter, see the ordinary matter recoil. Really difficult experiments, but a lot of effort going in to build these large underground dark matter detectors. Hopefully we'll resolve that problem sometime in the next few years. So it's pretty humbling. We began by noting that we live on a small planet around a small star, and it's one of billions in our galaxy, and the galaxy is one of billions of galaxies in the universe. And we've only occupied that space for 1/10,000th of the universe's lifetime, so that's pretty insignificant. And now we find out that everything that we know about in that little corner of the world is not the most important stuff in the universe. Everything else, 85% of the matter around us, is something else. And it even gets worse. It even gets worse because of Einstein's, what he thought was his great mistake, great blunder. There's a nice lesson here from Feynman. Of course, Feynman lived after Einstein, so Einstein didn't know about this comment from Feynman. But Feynman said, a theory that agrees with all the data is wrong because some of the data are wrong. And Einstein fell into this trap. He wanted his theory to match all the data. And so when he published his theory in 1916, both astronomers and poets thought the universe was constant. We've been talking about the Big Bang like everybody knows that, because we hear about it all the time. But if you go back to 1916, people looked at the sky static. It's sitting there. So Einstein has a problem because he has gravity. Gravity pulls on matter. If you put matter out there and it's a static universe and then you turn on gravity, it's going to start to slowly collapse. So he knew that his theory of cosmology wouldn't work the way he had written it. He can't add gravity and have a steady state universe unless there's something that keeps the stars in place. And so what he did was he realized that the only way to solve this problem was to add some resistance. And he said that he would add that resistance by actually giving pressure to the vacuum, an energy to the vacuum. And it's called the cosmological constant. So he took his left-hand side of the equation, the part that describes the curvature, and he added to it this cosmological constant to try to produce a steady state universe. Now that was a mistake because a few years later, Edwin Hubble tested the theory of the steady state universe by making a bunch of measurements with the Hooker telescope at Mount Wilson in Pasadena, and he discovered that there were stars and galaxies beyond the Milky Way. That was a first at that time. And he also found that they were moving away from us. It's not a static universe. And we can look at a little picture of that. Suppose that's us there on the Milky Way, and all those red guys are other neighboring galaxies. And this is what you would see if we watched for a long enough time. Those guys all receding away from us. It's like you're living on a balloon, and then somebody's blowing up the balloon, and all the points that you put on the balloon are steadily, all of them are moving away from one another. But from our perspective, if we're watching this from the Milky Way, that's what we see, receding away from us. Let's compare this with where we started before we blew everything up here, put the first graph on, and look at what happened. The guys that are close to us don't appear to have moved very far, but the guys that are far away appear to have moved away much faster. And when we look at light, when you see a train go by and it's got its whistle going, and then it passes you and you listen to the whistle, you can feel the Doppler shift, and the faster it goes, faster it goes away from you, the more the Doppler shift changes the sound. It's the same thing with light emitted from these stars. They're shifted to the blue, so that's why they're blue far away, dark blue and light blue closer. The light has been shifted from the Doppler effect. And so if you have some way of measuring distance, and that means you have to have some star, for example, that has a fixed brightness, and so when you look at a star and you measure its how much many photons you're collecting. You can figure out how far away. If you have some kind of standard candle like that, and then you can look at the blue shift of this sort, you can find out that the universe is expanding in a way. And that's exactly what Hubble did. And so again, I drew this from the vantage point of the Milky Way, but if I had picked any other galaxy and done the same thing, I would have gotten the same pattern here. It doesn't depend on us being any special position at all. So we know, in fact, this universe is expanding. So it's not static. Einstein had made his complicated equations more complicated than necessary, and he really regretted this. Gravity would still work against expansion. In an expanding universe, gravity still should slow things down. But it wouldn't. The fate of the universe wouldn't depend. Wouldn't depend on that. If the rate of the expansion were fast enough, gravity would slow it down, but it would still expand forever. If the rate were slower, eventually gravity would overcome the expansion, and then you'd recollapse into some kind of a reverse Big Bang. But actually, the ironies continued because it's very interesting now, since you know the universe is expanding, but you know gravity is retarding the expansion. Why don't we measure how it's slowing down? That would be a fun thing to do. And that was done over the last 10 years. And they did it by finding a better standard candle than Hubble had. So Hubble used a standard candle that was a star called a Cepheid variable. And what they replaced that with were very bright type 1 supernovae that you can see very, very far away. And they expected to see a decelerating universe because that's what has to happen if gravity slows the expansion down. And they found the data, and the data says you're not in the pink region, the decelerating universe, you're in the blue region. So even though gravity is acting against you, the universe is accelerating away from you. So that's pretty hard to understand. It means not only do you need the cosmological constant to balance things, you need to add enough cosmological constant that you can actually cause it to expand. That's the conclusion. So what we find out is that the rest of that circle is the dark energy. That's how much energy you have to put in the vacuum to explain the acceleration that we're seeing out there. So now the matter turns out to be only about 6% of the energy, mass energy density of the universe. And our visible world is just reduced to about 4% of the total energy and mass budget. Final thing I'll say is there are lots of other mysteries here. The mystery of the cosmological matter and energy is even more vexing than we've really presented it here. To the best of our ability, when we add up the amount of matter and we add up the amount of vacuum energy, it turns out to be 1. 1 in these units mean it's just enough matter that if this were an ordinary universe, it would expand out to infinity and be going at 0 velocity at infinity. It's 1 to about 0.5%. And it turns out it's very hard to do that. Because if you want the sum of the matter and energy now to be 1 today, and you were to go back times that we were talking about where we know the physics, like 1 second after the Big Bang, then it has to be dialed to 1 part in 10 to the 16 at that time to explain the fact that the density is 1 today. So somebody is dialing things just so that we have this strange state today. And this is kind of crazy because we've talked about the Higgs Field and Einstein's cosmological constants. Those are very different contributions to the energy. Why would they add up to be exactly 1? And of course, it gets much worse because you can think about the new mechanism for the neutrino mass that has to be added in there too. And it turns out even that the mass of the proton and the neutron just doesn't come from the Higgs, but also comes from interactions. So all kinds of things are adding up to give you exactly 1. That takes some explanation. We have some ideas, but it's pretty curious. There are lots of other conspiracies of this sort in astrophysics that really bother people because it looks like the world was very, very fine-tuned just so it looks like it does today for our benefit. So closing thoughts, our share of the universe is a remarkably small one. It's in the space we occupy in the short history of our species and the fraction of matter and energy that we actually even know about now. But in a way, it's kind of amazing. We had this little outpost on this one Earth, but we've learned a great deal about the inner workings of the whole. We've learned a lot about the big puzzles, for instance, that remain to be solved. Anyway, I want to thank Phi Beta Kappa very much for the chance to visit. I also want to thank the audience here in the University of Arizona.